What if I told you that the future of AI may no longer belong to electricity? Not faster GPUs, not smaller transistors, not even quantum computers, but light itself. Right now, inside some of the world's most advanced supercomputers, a completely new kind of processor is beginning to emerge. A processor that does not compute with electrons, but with photons. No massive heat, no insane cooling systems, no traditional transistor switching. Just light performing AI calculations at speeds that sound almost impossible. And for the first time, this is no longer science fiction. Because in 2026, photonic processors are already running inside real supercomputing facilities in Europe. And honestly, this may become one of the biggest hardware revolutions of our lifetime. Before we talk about photonic chips, you need to understand the problem forcing the tech industry to search for something radically different. AI is consuming absurd amounts of energy. Every new generation of GPUs becomes more powerful, more expensive, hotter, and dramatically more energy hungry. Modern AI data centers are now packed with thousands of GPUs running 24 hours a day. And here's the crazy part. A massive portion of the electricity isn't even used for computing. It's used just to cool the hardware down. Some advanced AI facilities spend up to 40% of their total power budget purely on cooling systems. Think about that for a second. Entire buildings consuming enormous amounts of electricity just to stop the computers from overheating. And as AI models continue getting larger, this problem gets worse every single year. The industry is approaching something engineers call the energy wall, because eventually, scaling AI becomes physically and economically unsustainable. For decades, computing advanced because of one famous principle: Moore's law, smaller transistors, more performance, lower costs. That formula built the modern computing industry. But today, silicon is approaching its physical limits. Transistors are now so microscopic that electrons begin leaking across barriers through quantum tunneling. At this scale, physics starts working against engineers instead of helping them. Then there's another massive issue: the memory wall. Modern processors constantly move data between memory and compute units, and moving data consumes enormous amounts of power. In AI systems, data movement is becoming almost as expensive as computation itself. So the industry has started asking a serious question. What if traditional computing architecture simply cannot scale much further? And that's where photonic computing enters the picture. Photonic chips replace electrons with photons. Instead of using electricity through transistors, they use beams of light traveling through optical pathways. And that changes almost everything. Light moves incredibly fast. It generates almost no on-chip heat. And unlike electrons, multiple streams of information can travel simultaneously through the exact same optical channel using different wavelengths of light. This technique is called Wavelength-Division Multiplexing, or WDM. Think of it like multiple invisible highways stacked on top of each other. Different colors of light carrying different calculations at the same time. Traditional electronics simply cannot do this efficiently. And the actual math happens through something called optical interference. When light waves meet, they interact. Some reinforce each other, others cancel each other out, and those interference patterns become the computation itself. The neural network calculation literally happens as light travels through the chip. No traditional clock cycles, no endless transistor switching, just physics naturally performing the math. And honestly, that's one of the most fascinating ideas in modern computing. One of the key breakthroughs enabling this technology is a material called thin-film lithium niobate. Researchers discovered it can manipulate light extremely efficiently while producing very little heat. That allows engineers to build dense optical circuits capable of handling enormous AI workloads. And here's what makes this even more important. Developers don't necessarily need to learn completely new software systems. Most photonic hardware companies are already building compatibility layers for *Python, *PyTorch, *TensorFlow, meaning developers can continue using familiar AI tools while the optical computation happens underneath. That dramatically increases the chances of real-world adoption. One company attracting enormous attention right now is Q.Ant, a German photonics company based in Stuttgart. In 2025, they deployed one of the world's first operational photonic AI coprocessors inside the Leibniz Supercomputing Center. In Germany, this was not a lab experiment. This was a real supercomputing environment handling actual workloads. Then in 2026, they deployed their second-generation native processing unit, and the benchmark improvements were massive. Reports showed dramatically higher throughput, faster AI inference, and enormous reductions in energy consumption. Some estimates suggested up to 90 times lower power usage, and up to 100 times greater effective data center efficiency. Now obviously, benchmark numbers should always be viewed carefully, but even conservative estimates suggest photonic hardware could fundamentally transform AI infrastructure. And that's why governments and research institutions are taking this very seriously. Because this technology is no longer theoretical. It's operational. And Germany isn't the only country moving fast. Research teams in China are rapidly advancing optical AI processors. Universities including Tsinghua University, and Shanghai Jiaotong University have already demonstrated extremely powerful optical systems for specialized AI workloads. This is becoming a global race, because whoever solves efficient AI computation could help define the future of computing itself. But photonic computing still has serious challenges. The biggest one is memory. Right now, photonic chips are incredible at computation, but terrible at storing data. There is still no practical optical RAM solution ready for large-scale deployment. So most systems constantly convert information between optical signals, and traditional electronic memory. That conversion costs time and energy. Engineers call this the conversion penalty. There's also another issue. Photonic processors are highly specialized. They dominate matrix multiplication, neural network inference, scientific simulations. But for general-purpose computing, traditional CPUs and GPUs are still necessary. That's why today's systems are hybrid systems. The photonic processor handles the mathematical heavy lifting, while silicon handles everything else. Even with all those limitations, photonic computing may still become one of the most important breakthroughs of the AI era, because the current trajectory of AI power consumption simply cannot continue forever. You cannot keep scaling AI endlessly by building larger GPU clusters consuming insane amounts of electricity. Eventually, the economics stop making sense. And that's why photonic processors matter. Not because they instantly replace GPUs, but because they may become the only realistic path towards sustainable AI scaling. My honest prediction? Between now and 2030, photonic coprocessors will likely become standard in supercomputing, scientific research, climate simulations, medical imaging, and large-scale AI inference. And if the memory problem eventually gets solved, this technology could spread far beyond specialized facilities. We may eventually look back at this exact moment as the beginning of computing's transition from electrons. Computers calculating with light still sounds unreal. But in 2026, it's already happening. And if this technology continues improving at the current pace, the future of AI infrastructure may look completely different from the silicon world we know today. Because the next computing revolution might not be powered by electricity, it might be powered by photons.